I'm here and we're going to begin the webinar. It gives me great pleasure to welcome you all to today's Power Grid Cybersecurity webinar brought to you by OPAL-RT. And my name is Tom Kirk and I'm a sales engineer here at OPAL-RT. And I'll be introducing cybersecurity. Unfortunately, our first speaker couldn't make it, so I'll do my best to do that part justice. And then I'll talk about real-time simulation applications, some basic cyber attacks, and also some of our users. And then that'll be followed by our keynote speaker, David Manns from the Pacific Northwest National Laboratory, who will be joining us from Washington State over the phone. So today's webinar will go as follows. We begin with the introduction to cybersecurity. We'll talk about real-time simulation, the application solutions, then cyber attacks, as well as some of the current OPAL-RT users doing work related to this field, and then finally our keynote speaker, David. However, I must add that at the end, questions will be answered, and the way you ask your questions is using the webinar interface. All you have to do is type in your questions, hit enter, we're going to receive them, and we're going to try to answer as many questions as possible today, so please don't be afraid to ask. If not, we'll always be able to get back to you after the webinar. All right, so when we think about cybersecurity, we think about smart technologies and the smart grid. So the reality is that as the grid is becoming more intelligent, it's also becoming more vulnerable to cyber attacks. And this in itself has motivated a new set of standards, namely NERC CIP standards. And first off, OPAL-RT is dedicated to providing open power system real-time digital simulation solution that meets the requirements of power system professionals across disciplines interested in cybersecurity. And how do we define cybersecurity? There are many definitions, and the first one I have here on the top left refers to an activity, process, ability, capability, or state where information communication systems are protected, defended, and against damage, unauthorized use, modification, exploitation. This is a very, shall we say, computer engineering heavy definition. But in reality, in the context of the power grid, it's not just about computer systems, it's about protecting critical infrastructure, which is what the second definition addresses. So this is, we're really considering both the cyber and the physical side of things. So that's exactly what modern power grids are. They're cyber-physical systems. They're composed of physical infrastructure and information infrastructure. And when we put them together, we get the modern power grid. So how is it becoming more intelligent? Well, obviously, there are new technologies. There's also a question of automation, such as the automation of substations, transmission and distribution systems. We're implementing more distributed energy resources onto the grid, into distribution, namely in the form of microgrids. It's also about advancing communication networks such that they're capable of two-way communication. And an important one to mention is the development and, shall I say, emergence of synchrophaser systems, which are mainly being used as monitoring tools, but are now becoming more part of the control landscape. And I should note that when we think of cybersecurity, we often think of malicious attacks, but NIST doesn't view it as so. They also view it as the potential for accidental flaws and faults in the system. So it's not just about attacks. But we'll talk about those anyways. And it should be important to note that the media has reported on several of these. Most of them are not published, it seems. And a couple that come to mind out of the dozens that have been collected over the years are, first off, Idaho National Laboratory Aurora experiment, which is an experiment, but they're showing here the capability of someone to hack into a communication network and blow up $1 million generator. And you can actually find this video on YouTube. It's quite interesting. Not to mention, there's the famous Iran's Stuxnet nuclear incident, where the Stuxnet virus ended up on that system, causing a great scare. And the Wall Street Journal actually found that FERC had analyzed the potential for a blackout due to the loss of substations, and they found that just knocking out 9 substations out of over 55,000 in North America could actually lead to such a long 1-year plus blackout. So NetScore has actually looked into some of the failure scenarios as well, and they've categorized them into different categories, including those that are due to compromised equipment functionality, data integrity attacks, communication failures. They also consider human error and natural disasters. So it's not just about malicious threats, it's also about those that could happen accidentally. And I mentioned earlier that NERC CIP standards are those for cybersecurity, and those are mainly focused on risk assessment and identification of critical and cybercritical assets. And how do we define those terms? Well, critical assets are assets that are actually physically responsible for delivering energy across the grid, whereas the critical cyber assets are those that manage those assets. So they're very closely intertwined, and categorizing assets can actually impact which standards are used to assess them, to implement them. So it's very important to consider these classifications. And along the same lines, the NIST cybersecurity guidelines for smart grids are actually also based on risk assessment. So if we think of risk as a function of threat, vulnerability, and consequence, and we ask ourselves certain questions, what threats are we concerned about? How do we evaluate the effects of vulnerabilities? What are some of the physical impacts? How do failures cascade? And finally come up with a number. Well, simulation actually turns out to be a really great tool to come up with a risk assessment. But what about real-time simulation? How does that play into all this? So that's what I'll cover in the next section. And if we look at a power system, we can come up with a layer analogy. So we can look at a physical layer, which is the actual generation systems, the lines, substation, inverters, loads. Above it, we have a lower level control layer that also has sensors and actuators. And then finally, we have what's especially critical for cybersecurity, communication and network and application layers, which deal with the infrastructure and software and so on that's used to manage those lower level systems. And at the top, we have a human layer composed of operators, decision makers. And the real-time simulator is really intended to model the bottom two layers and provide the interface via communication protocols. So by doing this in real time, we're actually able to simulate in 1 second of simulation time and 1 second of real time to test real systems at the top and including the following. So it's an extremely powerful tool with certain applications that could be covered within cybersecurity. The first being risk assessment. So penetration testing, determining cybercritical assets, identifying vulnerabilities, all things that could be done and are being done with a simulator. Research and development of systems. So what kind of systems are we talking about? Talking about cyber attack mitigation systems, situational awareness systems, network and communication systems, control monitoring ones, also synchrophaser ones. And potentially it could also be used to help organizations actually meet the standards specific and related to cybersecurity. So we got to think of this as a very versatile tool. And I'm going to actually pause briefly and we're going to put up a poll onto your screen. So you should see the poll. And what this poll asks is, which of these cybersecurity applications have you used or plan on using, or rather performing? So if you could just answer that, it would give us an idea of what people are interested in doing at their organizations. So we'll give a few more seconds to vote. All right, so we have roughly 80% of the attendees that have voted, and we'll be continuing. And in the context of real-time simulation, what is a typical setup? What could be used as a test bed? Well, first off, you need a simulator. And what the simulator does is it essentially is capable of modeling a power grid, and that power grid needs to be able to interface with external hardware and systems. So here, some of the hardware that we have in the diagram are phase measurement units, a protection relay, and a controller. But it's not just about those systems. It's also about higher level systems, for example, higher level control and monitoring applications. So it's not just about hardware in the loop compatibility, it's about system in the loop compatibility. And we also require, especially for synchrophasor applications, time synchronization. So a simulator must be able to sync to, for example, a GPS clock. And for high power applications, you can always throw a power amplifier into this loop. And one of the main benefits to this model-based approach, since you are modeling your power system using software, you can actually implement what are essentially virtual devices within your model. And considering how costly it can be to purchase hardware, especially if you require dozens of, say, phase measurement units, this is actually a very nice solution, especially for professionals that are concerned with the higher level applications and communication networks. And to be able to model such systems, you require rather comprehensive software solutions. And here we're showing a plot where the horizontal axis is showing essentially the frequency of transient phenomena simulated versus number of three-phase buses. So as the number of three-phase buses increases, we have larger power systems, and as we go towards the right, we have faster phenomena. So typically we think of EMT type software. So eMegaSim is a real-time software intended just for that. It's actually based on MATLAB Simulink and SimPower systems. And it has a very open API that uses Python, C++, and Java. This permits you to automate studies and potentially even link to external systems. Another class of EMT software is HyperSim, which was actually intended and is used for larger scale power system simulation. And this is a very detailed software that was developed by Hydro-Quebec, which also has robust testing capabilities in the form of automation. And last but not least, for phenomena that are around the frequency of the power grid or lower, we have phasor-based real-time simulation for real-time transient stability simulation. And what's interesting about this application is cybersecurity professionals are not always interested in high-frequency activity on their grid. They may actually just care about slower, lower frequency phenomena. And what you could do potentially with this, and because it's phasor-based, you can very easily emulate PMUs with the system. And one of the projects we're working on in-house is to create such a setup where we're using the IEEE 39 bus system as a base. We're connecting this to a model predictive controller via a PDC, and these, I should note, are all real devices. And all this is done at a software level here. So there's no hardware used at the lower level. And considering how many communication protocols there are now for the smart grid, these are truly the pillars of the smart grid. And the simulator requires substantial support for these protocols. So how do you use them? Well, we actually have a drag and drop solution for all our softwares. And what that allows you to do is, because you're drag and dropping protocol blocks within your models, you can actually simulate certain attacks and faults directly within your simulator. So this could actually be attractive to certain users for cybersecurity applications. But if you want to take it to the next level, considering how complicated, how important communication networks are becoming, if we look at this diagram on the right, we can see what NIST views as the future of the grid in terms of communication. This has obviously cybersecurity implications. It also has severe performance implications. It's also extremely costly to implement such systems. So what could potentially be used to minimize cost and still work on highly complex scenarios are network simulators, some of which are commercially and free for use available at the time. Next section will present a few cyber attacks that are of interest to power system professionals. The first one being denial of service. So DOS is commonly what renders search engines, social media networks unavailable. So a lot of us are familiar with this, but the same principle applies to the power grid. You could have viruses planted by hackers that essentially bombard a communication point and render services unavailable through it. And in fact, there's a well-known communication protocol that has been identified as being susceptible to such an attack. It doesn't just refer to that scenario though, it also refers to a physical attack. So wires being cut, potentially wireless jamming. Another one that's extremely interesting is the man-in-the-middle attack. And I couldn't say it better myself, so I'll use the words of Skopik and Smith here. It's an attack that impersonates two communication nodes by making them believe that they are talking together. So essentially, the attacker can see everything that's going on in your communication feed, and they can also inject spoofed packets, they can suppress information, they can actually record the stream of data that is being passed through it, and they can replay it and even modify those packets. So there's a lot of potential for chaos here. And last but not least, considering the emergence of synchrophaser systems, we now have to consider GNSS spoofing. GNSS refers to global navigation satellite systems, which includes constellations such as GPS and GLONASS. And why is this a concern? Well, phase measurement units are heavily reliant on time synchronization. In fact, the IEEE C37118 standard only allows a maximum of a couple dozen microseconds of pure timing error. So on the bottom right, there's a homemade, essentially, GPS spoofer from the University of Texas, and in it, you can see some basic PCBs that they've put together, but what they've done is actually logged on to a GPS unit, and they've spoofed it, and they've caused the phase angle measurements to deviate substantially and actually have broken the standard within minutes, dictated by C37118. And finally, you can see they haven't even removed the spoofer, but they've caused a massive angle difference in the calculation. This is relative to a system that hasn't been spoofed. So that has some considerable implications, especially if we're considering wide area control applications using synchrophaser systems. And how do we plan to address this within the real-time simulation context? Well, in fact, we've been speaking to experts in GNSS simulation, Spirent Communications, and we've been working on them and trying to bring a solution that meets the needs of power system professionals interested in this application. So we'll finish off by looking at some of the current OPAL-RT users that may have setups and applications of interest to this domain. And then, of course, we'll have our keynote speaker, so please stick around. And the first users that come to mind are KTH. So KTH have a very comprehensive wide area monitoring, protection, and control test bench. So they have a real-time simulator that's connected to real hardware in the form of PMUs, protection relays. They have amplifiers that create a high-power interface between the two. They have controllers in the loop that they've custom designed using basic National Instruments modules. They also have a communication network, which they can also simulate using a network simulator. And on the other end, they have in the loop applications that they've developed in-house, as well as commercial applications, all of which is also connected to the cloud and being streamed to partner universities so that they can all perform studies together. So it's an extremely comprehensive test bench for their applications. A more basic example is Virginia Tech University. This is from a paper that they released where they've modeled a simple power system and they wanted to test the ability of the communication network to pass information to an in-house design control center. And they've used OpNet as a network simulator tool. And you can see here in this graphical interface that they have the two connection points and they've set an arbitrary 100-kilometer line length between the two using OpNet. And they're adding background traffic. So the idea here is they want to simulate smart grid traffic. And what they've done is they've showed that as they increase essentially the utilization of the network, as they flooded the network with background traffic, they're actually increasing the latency of the system. So this is adding delay larger than the natural delay of the distance. And along the same lines, we have Ohio State University, who have a similar setup with a simulator. They have a communication system network simulator using OpNet as well. In their case, they're simulating microgrids, so they have a control server. And what they've done is essentially they've modeled their microgrid using the simulators, and their controller has been tested using a scenario where communication network simulation has not been introduced, which is this one. And then when they actually do that, they find that, in fact, the response time of the whole control system is actually substantially larger and cannot be neglected. So this is the kind of study that we see as being important for non-malicious threats. Now, a last example, and I like this one personally because they're not just doing a lot with it, they're also working on application development, and they're using what is called a PI server, which is an effective real-time server that permits them to actually connect to a whole host of devices, including the simulator, which they're using in this case for validation. But you'll note they're actually using it complementary to tests performed on a real-world system, and at the other end, they're actually working on cloud applications. So there's a whole lot of versatility that can be obtained from a real-time testbed. So that's it for me. I thank you all for your time and patience.